Okay, so let's continue our discussion still on the equation of motion. This time focused on the concept. What is inertial reference frame or inertial frame of reference? So let's recall in our discussion in kinematics about relative velocity, we introduced a concept called the frame of reference. Frame of reference. Relative velocity. This concept is very important to Newton's law of motion, especially the first law of motion. So to illustrate this point, consider a person on a bus which has a roller skate on both of its feet, and the bus is initially having a constant velocity, but it eventually gains an acceleration. So the purpose of the roller skate is that to eliminate virtually all frictional forces. So Fk is very small, such that no force will ever act on you. But since the bus is speeding up, you start to move in this direction, and if the bus starts to slow down, you start to move in this direction. Why is that? There are no forces acting on you, yet your velocity changed. The question is Newton's first law disobeyed? Was it disobeyed in this example? The answer is no. The point is that the bus is accelerating. The bus is accelerating with respect to the Earth, and the bus is not a suitable frame of reference for Newton's first law, because this law, the first law of motion, is valid in some frame of reference but not in others. And the frame of reference in which this law holds is called the inertial frame of reference, also called Newtonian reference frame. In contrast to Newtonian reference frame, there is what we call non-inertial frame of reference and inertial frame of reference, wherein the acceleration is 0, and in non-inertial the acceleration is not equals to 0. So the bus is not an inertial frame of reference, but rather a non-inertial frame. So the motion inside you, it cannot be described using the first law of motion in the first place, because the frame of reference in which you are using the first law of motion is not a inertial frame of reference, so it is invalid. It is not that the law is invalid, but the frame of reference in which you are using the first law to describe the motion is invalid. So here we have motion. The bus is accelerating. So the Earth is approximately at least in approximately a non-inertial frame. Even though the Earth, as we know, is moving in its axis and is also revolving around the sun, but those effects are quite small, or very small, when we are describing motions of objects that are near or located at the surface of the Earth. So Earth can be considered a good candidate for inertial frame of reference for objects that are near or earthbound. But for objects such as rockets or moons or other satellites, we don't use Earth as inertial frame of reference. Rather, we use the star, such as the sun. Okay, so continue in our discussion here on the bus. What is actually happening is that you tend to stay wherever you are. That is why first law of motion is also called the law of inertia, because first law of Newton is used to define the inertial frame of reference. So what is actually happening is that first you are here, then the bus starts to accelerate. So you appear or you seem to be moving in this direction, but actually with respect to Earth, you are just staying on the same location, because the Earth is in inertial frame and the bus is non-inertial frame. So in the bus, the acceleration is not equals to 0, but on Earth the acceleration is 0. So the tangential, specifically, the tangential is not equals to 0. The frame of reference in which you are in is accelerating. So another example is not in translation but in rotational. So let's erase this all. Again, let's view at the top. Let's say that this is the center, this is the radius, and initially this is the bus. Say this is the bus. Again. This is the bus. You are here, and the bus is moving circularly. Let's say that the tangential is 0, meaning the magnitude doesn't change, but the fact that the direction is constantly changing, therefore the normal acceleration is not equals to 0. Therefore the total acceleration is still non-zero because of a n. So what is happening is that as the bus moves circularly, it looks something like this. So it appears as though you are moving on the bus, but in reality you're just obeying the first law of motion, or the law of inertia. So again, the point here is that Newton's law of motion, the three laws of motion, apply only or hold only in the inertial frame of reference, or Newtonian frame of reference. So we talk about Earth as the frame, as the inertial frame of reference, but actually there are many other inertial frame of reference that can be considered aside from the Earth. So for example, let's illustrate this one as, let's say this is the Earth, we call it A, that is the frame A, and there's an object inside that which is called P, and the object is moving at a constant velocity, but with respect to A, okay, some constant velocity object P with respect to reference A. The A is assumed to be fixed, the fixed inertial frame, and there is another inertial frame, but we call it P, and this frame of reference is not fixed, but instead it is in translation, but with a constant velocity, So if there are two persons, okay, on reference frame A and reference frame B, okay, so according to the person A on frame A, the speed of the object P is this. But of course, to the person on B, the speed of the or the velocity of the P with respect to B is something else. Let's say we call it C sub 2. Okay, because B itself is moving. So using equations, relative velocity equations that we have learned from kinematics, we write that VPA is equals to the velocity of P with respect to B plus the velocity of B with respect to A, because P minus VB, if we can expand, and this VB minus VA, this will cancel out VP minus VA. So this is true. So let's concentrate on this one. So the velocity of P with respect to A is different. It's not equal. It's not just equal to the velocity of P with respect to B, but with some factor VB with respect to A. So the interpretation of this is that both observers disagree on the velocity of P. They both disagree on the velocity of P. So for example, according to A, the velocity of P is, let's say, 10. According to B, the velocity of P is, it could be 5 or it could be 50. Because again, B is in motion. So again, both first observers disagree on the velocity of P. But they don't disagree that the acceleration of P is 0. Meaning that the velocity of P is constant. It doesn't matter if it is 10, it doesn't matter if it is 5 or 50, but they both agree that acceleration of P according to A is 0 and the acceleration of P according to B is 0, meaning it is constant, whatever value is that to the observers. And because of that, the acceleration is 0, therefore the forces that act on the object P is also 0. So what this means is that the state of rest or motion of a body is not very different. It's not very different because both can occur when the vector sum of forces that act on the body is 0. Okay, so even though, let's say, VPA is 0, so according to observer A, VP is not moving, therefore the forces that act on P is 0. Yes, that is correct. And acceleration on P is 0. Yes, that is correct. But according to B, since its frame of reference is moving, this is moving, example, VB is moving, let's say, at 20 meters per second. So according to observer B, P is also moving at 20 meters per second. So they disagree on the velocity, but they agree that P according to observer B is still 0 because it is moving in a constant velocity. Therefore, the acceleration of P is still 0. So they agree on both on this except for the velocity. It is because they are both inertial frame of reference. That is, the acceleration of A is 0 and the acceleration of B is 0.